In the previous video, we proved a theorem that says if f is a field, then the only ideals in f are the trivial ideas, 0, and the field itself. In this particular video, I want to look at answering the question, is the converse of this theorem true? But the first thing is we have to figure out how to state the converse. So let's look at how to state the converse. Because it turns out that that's not trivial in this particular case. So the thing that I want to do is I want to be thinking about what is a field, because our converse is going to need the end of this thing being something as a field. So I want to think about the formal definition of a field. And the formal definition of a field that our author uses in the textbook that we're currently using includes all of the following things. R is a field means, so if and only if, 1, R is a commutative ring. Second of all, R has to have a 1. R has a multiplicative identity. And the third property is that every non-zero element has to have a multiplicative inverse. Now, the author implicitly and it sometimes explicitly states that fields have to have at least 2 elements. In other words, he insists on having the 0 inside of a field not be equal to the 1 inside of a field. So the 1 and the 0 are different elements, which is going to say that any field is going to have at least 2 elements. And I kind of want to analyze why we need that in some basic sense. What does this buy us? So let's actually look at rings that only have 1 element. So a ring with only 1 element. So our 1 element is going to actually be the 0. And it's going to have a plus table that looks very boring. 0 plus 0 is equal to 0. And because multiplication has to be closed, 0 times 0 is also going to have to be 0. But this particular table will say that 0 acts as a multiplicative identity. So this says 0 is a multiplicative identity as well as an additive one. And since 0 times 0 is equal to 0, this also says that 0 inverse is just going to be 0. This table says minus 0 is going to be 0. And so in this ring with 1 element, we do have R is commutative. We do have R has a multiplicative identity, but the multiplicative identity is named 0. And we do have R has multiplicative inverses. There's only 1 element in the ring, and 0 inverse would be equal to 0, since 0 times 0 is equal to 0. But this is really not, it doesn't behave the same way most fields behave, because the 0 and the 1 in this particular ring are one of the same thing. And so the author does not want this ring with only 1 element to be considered a field. So we have a formal idea, a formal definition, if you will, that the ring with 1 element is not going to be considered a field by our author, just by definition. So when we want to start crafting the converse of our theorem, we need to keep in mind that the ring with one element is a commutative ring, and it has a multiplicative identity, and it has multiplicative inverses, and the only ideal in the ring with one element is the ring itself, which is also equal to the zero ideal. In other words, if you've only got one element, you only have the trivial ideal. And the trivial ideals happen to both be the same ideal. They are both the ideal generated by, the principal ideal generated by zero. And so we have to keep all of this in mind when we're trying to craft a converse of the theorem. So let's now look at our theorem again. If F is a field, then F has only the trivial ideals, the zero ideal, and F itself. One possible way of crafting a converse, and I'm going to call it converse 1 because there is more than one way of crafting it, is to take the fact that we've got that one element zero ring running around and put it into the conclusion of the theorem. In other words, we're going to let R be a commutative ring, and we're going to go ahead and assume that we have a multiplicative identity element. If the only ideals in R are the trivial ones, namely the zero ideal and R itself, then R is either equal to the zero ring or R is a field. Now, I want to actually think about the logic of this particular statement before trying to prove it. And the logic of this statement is a statement that says a hypothesis, and the hypothesis is all of this mess, implies one conclusion or a second conclusion. Now, in symbolic logic, when you've got an implication that has this structure, it is logically equivalent to assume that you have not got one of the conclusions, but you do have the hypotheses. So you're going to assume that you have H and the negation of one of the conclusions, and you want to force the second conclusion. That is a standard proof technique for this kind of an implication. So what we're going to do to try and prove converse 1 is the following. So here is our proof of converse 1. We're going to assume R is not the zero ring, but the only ideals of R are indeed the zero ideal and R itself. And of course, we are also assuming, by the way, that we've got a commutative ring with 1. So let's think about what that says. And so we have the situation where R is a commutative ring with a multiplicative identity element, and we know that R is not the zero ring, and of course R has only the trivial ideals, so the zero ideal and R as ideals. And I need to make my writing clear there. Now, I want to remind you of a problem on a problem set that you did earlier in the semester. You showed that, that if R is a ring with an identity element, and the identity element inside the ring is equal to the zero element of the ring, then the ring has exactly one element. It is the zero ring. The contrapositive of your problem, the contrapositive of what you showed, is that if R is a ring with a multiplicative identity element and R is not the zero ring, then we know that the 1 inside the R is distinctly different from the 0 inside the R. And we're actually going to need that contrapositive to finish off the proof of the converse of the main theorem. And so I want to kind of think about what this means. What we have, of course, is that R is a commutative ring with 1, and it's not equal to the 0 ring. And we know that we only have these two ideals. So I'm going to essentially look at things along these lines. Let's let A be any element of the ring that is not equal to 0. And what I want to note is this. First of all, I want to note that the principal ideal generated by A is, by definition, R times A, where R is ranging over all the elements of our ring. And of course, 1 is inside that ring of ours. Hence, what I know is that 1 times A, which of course is equal to A, has to be inside this principal ideal. And that's enough to say, since 0 is not equal to A, and A is inside this principal ideal, that is enough to tell us that this principal ideal is not just the 0 ideal. And that tells me that the principal ideal generated by A is actually equal to all of R. But now I have to think about this. But I know that 1 is inside my ring. And since the ring is actually equal to the principal ideal generated by A, we know that 1 is inside the principal ideal generated by A. And that implies that there exists an R inside my ring R, such that 1 is equal to R times A. But our ring is commutative, so R times A is equal to A times R. And this is enough to say that R is equal to A inverse by the definition of inverse. And what we now have is every non-zero element of the ring R has a multiplicative inverse, and that means that we know that R is a commutative ring with 1, and all elements, all non-zero elements, have a multiplicative inverse, and we know that the 1 is not equal to 0. And that says R is a field. And that completes the proof of our converse.